So I think I should be here, perhaps. So it's a pleasure to be here. Thanks very much. So I'm going to talk to you about a project that we call Ziria. It's a project about taking ideas from functional programming, not functional programming per se, but you'll see what I mean, and applying them to wireless physical layer programming. So the physical layer of wireless protocols is the part of the protocols that typically takes the samples from the RF component and converts them up to a bit stream to be processed by the MAC layer. This is joint work with some great people: Gordon Stewart, he's student in Princeton; Mahav Goda, PhD student at UIUC; Jeff Mayland from Drexel; our undergrad Christina Luengo; and Anton Ekblad, who is a local. And the project started when Božidar Radunovic, who is a systems person, approached me and proposed this problem. So I'm gonna take a slightly long introduction because I want you to understand the domain and where this project comes from, really. And it's about programming software radios. It started basically for the need to program software radios. So Božidar came to me and he told me that there's lots of recent innovation in the physical and the MAC layer of wireless protocols. And the communities, relevant communities, Mobicom, SICOM, and SDI, that's where you're going to see lots of papers about this. And people have been experimenting on their ideas and designs using software-defined radio, software radios sometimes. Software radios, I mean, the principle is very simple. Typically, you have some RF component that sends samples through PCI Express to a CPU or to some dedicated core, and all or most of the physical and MAC layer processing happens on the CPU. So. So the lower levels of the protocol are defined themselves using software, which was not something that was common 5-10 years ago. So popular platforms that people are using is GNU Radio, which is a relatively easy to program platform, provides lots of libraries. It was developed by radio amateurs in the beginning. It was a perception that it's slow. The first real-time GNU Radio Wi-Fi receiver appeared last year. But it is catching up. And the other platform, one other platform, and apologies if there are people in the audience that have their own platforms for software radios, is SORA, which is a C++, heavily depletized C++ library, plus a custom hardware. And I think that it was this project that first showed that it is actually possible to do the physical layer processing on a CPU. And you just have to connect the specialized hardware through PCI Express, and you have all the latency and throughput requirements that you need. You can achieve them. However, in order to do this, you have to do lots of manual optimizations in the code. So if you look at the SORA implementations, they are very, very low level. And it's very hard to modify. As a result, it's very hard to modify the SORA pipelines. Components have shared state. Pipeline widths are kind of provisioned manually. However, the code is extremely fast, it's blazingly fast, as you will see later on. And they do provide some libraries as well. So, the problem, what is the problem? Well, essentially, what people have been complaining against FPGAs, and that led to the popularity of software platforms, which is the designs might be error prone, or you might have latency sensitivity issues in your design. You have to wait for a number of cycles, or that the code semantics is very tied to the underlying hardware execution model, so it's not portable, and it's hard to maintain the code. And you also have to learn hardware to do research on wireless. So this kind of complaints that people had. Actually, it turns out that this, in the current state of affairs for software platforms, these arguments are valid too. So this kind of undermines the very advantages of software. I have to say, a bright point in this space was AirBlue, which was actually a hardware synthesis platform, which identified these kind of topics and said, we're going to try to do better. We're going to try to offer a latency insensitivity designs and high-level programmability for hardware. This hasn't picked up as much, and I think one of it is because, well, it is an FPGA platform, so it's kind of harder to get access to it. So I would say that Ziria, our project, has similar goals for software implementations. Let's make the software be what it's supposed to be, which is easier, more configurable. So I just want to give you a glimpse of some manual optimizations that are done in this SORA platform. this is some code that computes a lookup table for computing a scrambler. So a scrambler is generating a pseudo-random sequence of bits based on your input stream. And this code here takes that little computation that gives you the pseudo-random sequence and effectively computes all possible values of that pseudo-random sequence for all possible inputs, and does that statically, so that at runtime we just look up the value of this computation from a lookup table. So this kind of manual code, and it's a bit, there's lots of manual bit fiddling code like that in the SORA implementation. That's kind of one example. Another example, which I'm going to get back to later, and I mentioned before as well, is that there's manual provision of data flow pipeline widths. How big an array should be that you should receive from the guy upstream in your processing pipeline. And that makes it very, very difficult to port SORA, to modify SORA. Now, another problem, so this is kind of the low-level problem. There's actually another dimension of the problem, which is the high-level problem. So the data flow abstractions that are used commonly in these systems is that of a vertex in a data flow graph. You want to implement a block, you implement a vertex. A vertex has an input and an output, and that's it. So this is reasonable, or maybe multiple inputs and multiple outputs, which is reasonable as an abstraction of the execution model, because a data flow model kind of naturally lends itself to low latency implementations. I mean, you can choose a scheduling, you're very flexible. As soon as data comes in, you can just pump them out. But I claim to you, and I'll try to make a big deal in this talk, that it is unsatisfactory as a programming model, and we can do better if we have a high-level abstraction in terms of compilation, actually. So what do I mean by that? Why do I say it's unsatisfactory? And I will get back to this slide in more detail. It does not expose when is the vertex state initialized or reinitialized. So Wi-Fi protocols sometimes, very often, talk about the initial state of a component and how it's updated through time as it's processing an entity, like the packet header or the actual packet. Under which external control messages can a vertex change behavior. For example, suppose we have like a decoder that's working with some specific encoding parameters, and then we want to change them at some point during the processing of a packet. Or how can a vertex transmit control information to other vertices? So you see here that I kind of there are kind of two dimensions in these programs. There's a dimension that talks about where the bits and bytes are flowing, how they're processed through the system. But there's also a dimension which is how do these extra off-band, out-of-band kind of control messages move around, and how do you ensure synchronization? And the programming model that says, oh, that's just a node, and I'm going to find some other way to communicate these out-of-band messages, is just not satisfactory. So let me just put you another example here from SORA as well, that highlights some of it, not all of it really. So this is the implementation of a block called a rate selector block. So it's kind of it chooses components downstream based on some rate parameters. And here you're going to see a shared state, which is this CF11A RX vector. That's a state shared with other components that are upstream somewhere, somehow. But you don't know when these guys are initialized and who mutates this variable, and it's very, very hard to know exactly the semantics of this variable. So it's also a bit verbose, so that hinders fast prototyping. Now the other thing on the right that I want to mention is that one problem is that this is a reset function of a specific vertex. We're supposed to kind of reinitialize the vertex. Of course, we don't quite know when it is going to be called, but we know that it is going to call 1, 2, 3, 4 guys downstream, depending on the data rate, and that means that the implementation, the very implementation of a node of this vertex, relies on placing it in the right place. It's connected to 4 guys downstream in the pipeline graph that you're creating. Just kind of mixing the implementation with where you're going to put him in. So we can't use this guy in something else. So now I will have one slide which is going to be very, very important throughout this talk, which is going to make it explicitly clear what do I mean by state and what do I mean by control. This is a dummy skeleton of the Wi-Fi receiver, of a Wi-Fi receiver. So the black line here means that the input data stream comes in, and the input data stream is complex samples from the RF component. So we have this detect STS component. So at first, although you're going to see all of these guys being connected together, at the beginning of time, it's this guy who is active, the detect STS component is active, and this guy is trying to detect if there is some transmission, if there is some packet there. Now, he's going to be working, he's going to be updating his own internal state, trying to figure that out. And at some point in time, he's going to say, sure, I found that there is a packet here, and I'm going to transmit some information that signals that, like a small structure. And this guy is going to start, and he's going to do a channel estimation. So he's going to take over the rest of the stream that's coming through. He's going to take over, and he's going to try to estimate the effects of the communication channel, because we would need to invert those effects when we decode later on. So at some point, he's going to be working, and at some point, he's going to say, okay, fine, I know there's some information about the channel, because I've read a few more bits in the packet, and I can use those to identify the characteristics of the channel. And here's a data structure explaining what the channel is doing. And I'm going to pass him to these guys here. So at that point, this guy is going to take over the invert channel and the decode header. So all of the bytes, all of the complex numbers are going to be passed through the inverter and through the decode of the header of the packet. And then at some point, he's going to say, oh, I decoded the header. Here is some information about the payload. We call this kind of packet info. And that information, for example, contains the modulation parameters or the encoding parameters of the actual payload, which could be different than the header in Wi-Fi. And then this guy kind of takes over. And so the rest of the bytes flow here in the end. And the channel is inverted, of course. And then we decode the packet using these parameters. So I use these kind of lines, these horizontal lines, I call them control values, because they are kind of out-of-band signals that one component sends to the other to notify that something is happening. You can start working, or you take over, or you initialize yourself and start working. So this is going to be a very, very important slide. But I hope it makes it clear what I mean by state and what I mean by control. Okay, so, yes?
Sorry, before we get too far away from this, can you say why Streamits attempted this with teleporting control their teleporting messages for the controller?
So I think
is that sufficient?
I think they it is sufficient, but teleport messages, they have a rather complicated mechanism of enforcing synchronization, and actually it's not obvious from the data flow graph where the teleport messages are. So you have to go inside the implementation of a component to actually figure that out. Whereas I claim that this block should be kind of like a first-class citizen. It should be like upfront in your design. It should be very clear. Yeah.
Are these components running concurrently, or?
No, well, some of them are, but not all of them are. So, for example, I explained the dependency here. So, in our implementation, this component this component has to run before this component, because you have to see if there is transmission. If there is transmission, you have to do channel estimation, the rest of the packet. And then you have to do these guys. Now, the inverter and the decoders, they can run in parallel. And the inverter and the decoder can run in parallel. And actually, the code contains more stuff that could run in parallel. So, along this axis, they don't run in parallel. Along this axis, they can run in parallel, roughly speaking. But let's get back to that a little bit later. So, all I want you to understand at this point is this out-of-band signaling stuff. Which I think might be probably clear. So I think it's a great opportunity to use functional programming ideas in a high-performance scenario here. We can provide better data flow abstractions that actually capture state initialization and capture these kind of control values. And we can use ideas of functional programming to better automate some of the optimizations. So I'm going to talk to you a little bit about this. So Ziria is a language that it's not embedded. I will go into this question in the extra time if you ask me. For bitstream and packet processing, it offers programming abstractions that are well suited for wireless physical layer implementations. Have an optimizing compiler that generates real-time code. It's developed in MSR Cambridge. And I just want to give you a very, very quick demo of a video that we recorded in Cambridge.
Okay, so this is our experimental setup. Here we have two SORA boards, which are connected to two PCs down there, and they're connected to these two screens. This is a SORA transmitter, which is actually now transmitting packets, continuous packets in 6 Mbps. And here is the SORA receiver, which is receiving packets. And you can see that at the bottom there, that it has been receiving almost all of the 1,000 packets being sent with
99,000
packets being
1,000 success rate in reception
missed because of errors. And the packets are 1,600 bytes, and then they're sent using modulation 0 and 20 remaining 6 Mbps. So now I'm going to change the transmission rate here. I'm going to use it, put it to 18 Mbps. And now going back there, you'll see that here things have changed. We do have some more miss errors here, but still in the 90s, 90% of received packets. And again, these are very large packets, 1,600 bytes. It's actually larger than the proper MTU size.
It's kind of a small demo. Just wanted to show you the thing kind of working in action and achieving like a packet successful reception rate of like above 95%, and in small rates actually 99 these days. The language. It's kind of two level language. It has the lower level consists of is an imperative C-like language for manipulating bits and bytes and arrays. An interesting design point is that array sizes are statically known, and it is aimed at electrical engineering crowd. So we do not want to make it look very alien to electrical engineers. So people that are familiar with C and MATLAB. On the higher level, there is a monadic language for specifying and composing string processors, which tries to identify control and data flow distinctions. And our runtime implements a low-level execution model, which is inspired actually by Stream Fusion in Haskell, and provides efficient pipeline parallel execution. So let's look at what the abstractions are of this language. So there are basically two abstractions that replace the uninformative vertex in a data flow graph abstraction. Okay, so the first abstraction is the notion of a stream transformer. So a stream transformer is a component or a processing block, if you want, which takes messages of type A in and emits messages of type B out. And I have this capital T here, which is like a type index. And by that I mean I identify in the type system that this guy is a transformer. So this has nothing special. It's what you would expect in a data flow graph. You take messages in, you emit messages out. On the other hand, we have a stream computer. A stream computer is, which we identify with this type STCVAD, is a component that is supposed to be taking messages of type A in and processing them, and spitting messages of type B out. But at some point in time, he's going to say, I'm done, I'm finished processing, I don't want to process any more data from the input. And here is a control value V for you. That's why V appears in the type as well. So take messages A in, emit messages B out, and at some point in time finishes and gives you back V. Yes.
How many messages? Synchronous data flow or asynchronous data flow?
So it's up to his own internal state.
But it's not part of this type or the specification.
No. That's not part.
Fixed data rates.
No. Most of the components will have fixed data rates in the end, and we'll get back to that when we talk about vectorization. So I will say that types are similar to, but a lot similar than types that you have seen perhaps in Haskell pipes libraries, if you're familiar with that. Now, let me just give you some examples. The map combinator. So I'm going to give you some primitives now that are transformers or computers. So the map combinator takes an ordinary function, A to B, and creates a transformer that receives messages of type A and emits messages of type B. Now, repeat takes a computer who takes messages of type A in, emits messages of type B out, And at some point in time, this guy says, oh, I'm finished, here's a unit value. And basically restarts him when he finishes. So the end effect is that the whole component becomes a transformer. So you can imagine that, okay, if I want to receive like many packets, for example, I might create a computer that kind of does all the processing for one packet, and I'm going to put a repeat around him, and there I have my processor for many packets. Now, the simplest possible computers that we have is a take computer, which immediately takes a value of its input stream, A, and gives it back to you in the control channel. And emit is something that you give him a value, and he just pushes that value in the data channel. And he immediately returns, so he's a computer. So he just pushes it and says, I'm done. Now, the interesting bit is that these abstractions, the computers and transformers, we can compose them along the data path and also along the control path. So up here, we have this power combinator, which accepts a transformer from A to B, and a transformer from B to C, and gives you back a transformer from A to C. That's pretty natural. However, its type is actually overloaded, so we can actually use him with a computer that is taking inputs A and B's, and a transformer that takes B's to C's. But at some point, this computer is going to terminate, and what are we going to do? We're going to produce a computer that actually terminates, but streams from A to C. So similarly, there's kind of the symmetric version of this one, where we have a transformer and a computer, and the result is a computer from A to C. So we call this composition along the data path. And functional programmers and experienced people with types might say that there was a nicer way to kind of combine all these things into one particular type. But let's talk about this later if someone is interested. Now, other than composition in the control path, we have composition in the data path. We have composition in the control path. And interestingly, this type here forms a monad. So if we have a computer that is supposed to be streaming, taking input messages A and emitting messages B, and at some point he finishes with a value V, we can take that value and use it to configure and start this guy here, who could be anything. It could be either a computer or a transformer. Takes messages of type A as well, emits messages of type B as well, and the end effect is that we get an STXAB. So you must have noticed in my previous slides that I didn't, although I described a computer like this here emitting a value, he didn't have an arrow in for being configured. That is because the value in comes for free from the bind of the monad. It's like a parameter in the closure. And of course, there's the return of this monad, which is, oh, you just have a value, you give him a value, and he just gives it back to you in the control channel. I just want to say that since we are in Sweden, this is reinventing a Swedish classic, which is a monad that was first introduced in a similar form in the Fudgett's joint thesis in 1996. I think we've rediscovered this, but it's kind of nice to see an old functional idea, brought back to life again. Right. So I want to kind of mention, we will get back to this, but this is kind of funny, right? Because I didn't give you any guarantees about the race of the components. So when this guy terminates, what if this guy, for example, wanted to kind of spontaneously emit some more C's? Are we supposed to emit them, or are we supposed to not emit them? The design principle that we're going to follow throughout is that pipelines are drained from the right. So only when this guy has nothing more to emit are we going to go and ask for data from this guy here. Similarly here, but here it's not as important because okay, he's going to terminate anyway. So, all right. That's kind of a subtle point that I will return to later on. So, composing pipelines and diagrams. We are Haskell. Well, many of us are Haskell programmers, so we use monadic do notation. in Ziria source, we call it a monadic sec notation, because sec for sequencing the operations. So sec of x takes me 1 and me 2, and then m2, is just m1, and then bind that to me2, to m2. So here's kind of an example of how we can stage more complex pipelines. We have C1, who is a computer. All of his data is passed through T1, and the result is that he is a computer. So here we get a value from him, and that value it lives now in the closure of T2 and T3, which is just two transformers. So the data is going to flow like this. In the beginning, we're going to be processing through that guy. When this guy is going to say, I'm done, this whole left sum component is going to say, I'm done, and he's going to produce a value V. And then the rest of the input stream is going to flow to the second component of the pipeline. So it's like a switch. Like the data is flowing on the left in the beginning, and then to the right, and then to the right, and then to the right. That's the way to think of it. Okay. So now you will. Now that I've given you the language constructs, you will see that it's very easy to capture this kind of RX pipeline in code, because we can just say, well, it's just a sequence of detect STS, that guy, and here we get a packet start. And then we do channel estimation, okay, and then we get some channel info. And then we do invert channel, and all of the bits of the invert channel, we pass them through the decode header. And as a result, this whole thing is a computer, and we get back a packet info. And then we invert the channel again for the rest of the stream, and we decode the packet. So this is the Wi-Fi RX skeleton in code. And I think quite faithfully captures the diagram. Of course, I drew the diagram. So, one thing that I haven't mentioned is how do we plug in this low? I mean, I talked about this kind of a two-level language, and I focused on the abstractions. So how do we plug in low-level imperative code? Well, we have a language construct as well. So in reality, this is just done with return of some big imperative expression that eventually reduces to a value, and that's the value we return. In source language, we use the do notation. We use a do notation to kind of lift imperative code. But in terms of the combinators that I showed you before, this is just return that accepts a computation that's supposed to run and give you back a value. So this part here, this blue part, is part that comes from the low-level language, and the extra stuff here is kind of high-level language. So here you see there is a state for this component that we initialize when we enable this guy in the pipeline. That's when scramble state takes its value, and then forever in this particular case, we take one bit, we do some imperative computation, and we emit y. So now. I just want to give you this as a small taster of what it looks like to program the low-level parts and the high-level parts. So we mainly target CPUs at the moment. So I'm going to talk to you a little bit about the CPU execution model. How do we compile the code? How does it run? So in effect, it's very simple. Every STCV component. CVAB component compiles to three functions. One function initializes the state of the component. So I'm writing this kind of informally here as in the state monad. But I guess you kind of understand what I mean. So we initialize the component, and then we provide a tick function and a process function. And a tick function really asks the component if there is some result already there, or the component needs some more input from some guy upstream to be able to process. So there are some components that do not need anything to be able to process something. For example, if I emit, I do not need anything from the input. I can just emit. But if I am supposed to take, I need to read something from my input to be able to take. In the next slide, I'm going to explain this in more detail. But the compilation task is, the business of the compiler is compose, tick, and process and emit compositionally from smaller blocks. So you start, with a tick and a meet and return, and you just build up, build up, build up. In the end of the day, you have one tick and one init and one process function. Now, the runtime main loop is the following. So we have a tick at the top level. So we ask that component. We say, what's your answer? And he says, I need input to be able to do anything. Okay, if he needs input, then we read alpha from an input, and we push that alpha with the process function of that component. Now the process function will give back a result. The result will be either skip. I just updated my own internal state. I'm not going to do anything with this component. In which case,
go back to the previous slide.
Yeah.
Where did skip show up? Or process returned.
Process returned a result.
Oh, so a result which is down there.
Yes. So skipping. I might have a mistake here because skipping goes to tick in reality. So if I skip, I should kind of start again. So I think this arrow should be to tick, not to process. So can I raise this arrow here? So, or I can actually yield a result, and if I yield a result, what do? Well, I write B to the output, and I go back to tick, so like the main loop kind of starts again. Or I can say I'm done, and in which case I write B to the control output, and basically I'm done. Done means I'm finished. Now, if when we tick the component, we say tick might have already a result there, because it was computed from a previous iteration. And it could be a skip. Actually, skip is not very common in the implementation of the blocks. It's not very common that you just tick a component and says, oh, I'm not going to do anything with you ticking it. But for the sake of keeping the same data type here, I take it. Or it can actually yield. For example, emit will directly yield if I tick him. And then we write to output and then go back to the loop. Or it can say, I'm done, and then we're finished. So that's kind of the main loop. Yeah?
Are all the components ticked at the same time?
I mean, there's only one tick and one process and one init function at the end. The way you're going to compose them, so the purpose of the compiler is to compose a scheduling strategy, if you want, from the underlying tick and init and process all the way up.
It's strictly sequential, not multi-core code you generate that way.
It's strictly, yeah, exactly. So I'm showing you strictly sequential code at the moment, yes. So the decisions for kind of building this up comes into two questions. Like, how are we going to tick and process C1 par C2? And how are we going to tick and process C1 semicolon C2, a sequence of C1 C2? And the idea is what I explained before, really, which is that to tick C1 C2, to see does that component have something ready to emit, we tick the rightmost component, the guy that's the rightmost guy in the pipeline, to drain him. If he says that he needs input, then we go and we tick the first component, C1. And if he says that he needs input, then we take some input, and we push it through C1, and we push it through C2. So basically, ticking goes from right to left, processing goes from left to right, yes. And the reason is our design decision that in the single-threaded CPU case, we want to avoid introducing queues as a result of compilation. So we always kind of go and drain stuff out before we push more things in. And that has an overhead, but not very important in practice. So now for ticking a sequence, basically, after we initialize this component, we start ticking and processing on C1. And at some point he says, I'm done. And from that point on, we tick and process on C2. So we initialize C2, and then we tick and process on C2. Okay. That was kind of the execution model. The compiler exploits the monad laws for optimizing some of these things away, fuses part of the data flow graphs, the low-level compilation trick that we use, try to reuse memory and avoid redundant memcopying. We try to compile expressions to lookup tables automatically, automating the manual code that I showed before. And we implement this pipeline vectorization transformation, which I'm going to talk a little bit more about. And we actually provide pipeline parallelization for top-level pipelines. So for pipelines where you can actually express all the parallelism at the top level at the moment. So this is work. We've done this, but we're extending this, so it's work in progress. What I want to talk a little bit more in this talk about is the pipeline vectorization in the next 5-7 minutes or so, which is something that I consider a very nice optimization that we perform. So the problem statement is the following. Given a component that's going to be processed taking messages A and emitting messages B, we want to rewrite it to a vectorized component that takes a chunk, an array of n elements of A, and emits an array of m elements of B for some n and m. So our business is how do we figure out the n and m, and how do we rewrite the component? Now, why do we want to do that? We want to do that because fatter pipelines like this mean that we have lower data flow graph interpretive overhead. Instead of going and ticking the graph for every single bit, for example, that has flown through, we can tick every 64 bits, let's say, or every 32 bits. Also, array inputs versus individual elements means more data locality. And especially for bit arrays, this enhances the effects of lookup tables, and I'm going to get back to this specific point. Now, I just want to mention here very briefly that this is a manual optimization in SORA, and it makes code very incompatible. It makes SORA code very incompatible with and non-reusable in other pipelines. So we want to be able to write the component in a very natural, kind of, let's say, element by element fashion. And depending on the pipeline that we stick it in, we want to figure out the appropriate width and have the compiler do it for us. For instance, some of the encoding and decoding components decode the header of the packet, but also decode the payload of the packet. So we'd like to have to write the encoding decoding components just once and stick them in the pipeline, and we're going to get different vectorization widths in different places of the pipeline that we're using. Let me just briefly say how we do this. We compute, conceptually, every component has a feasible vectorization set, like a set of feasible vectorizations. Vectorizations are not going to change the semantics of the program. So for example, here we take 80 elements from the input, and we emit 2 elements to the output until completion.
Was this before vectorization?
This is before vectorization, yes. So it takes 80 minutes, take a single bit at a time, 80 times. It's different than that take that I described before.
So you need input 80 times if you manage.
Yes, exactly, yes. So assume that we have, for every computer, now I'm talking about computers, not things that are repeated. Assume that we have what we call a cardinality info, which is the number of values the component is going to take and emit before he actually returns. He's a computer, he's going to return. Suppose that we know this information. We call this here, we're going to take 80 elements in, and we're going to emit 2 elements out. This goes back to your rate value. Now, the feasible vectorization set, one choice for the feasible vectorization set for this component is, well, just take all the divisors of 80 and all the divisors of 2. Because you can take, let's say, you can take 10 times, you can take arrays of size 10 or size 8. You can stick them in an array of X, and then just emit an array of size 2. So that's kind of a feasible vectorization set for these guys, for the computers. So we have converted a component effectively. So our compiler is going to figure that out, and we'll convert a component of that takes int and emits int to a component that takes 8 ints and emits 2 ints. Okay, that's okay. So actually the implementation keeps feasible sets and not just singletons. It doesn't just say, oh, that should be the vectorization. And the reason is because we kind of need to combine them together in a well-typed fashion. So if C1, for example, here has 2 possible vectorizations. One that takes 80 and 2, and one that takes 16 and 2. And the other guy, C2, has 24 and 2 and 16 and 2. We should pick as the vectorization candidate for the bind the one that chooses that from that component and that from another component, because there is no other well-typed solution. So we have to choose C1, V1, C2, V2. So we have to keep kind of sets around the combine, more constraints around the combine if you want.
The seek does this sort of switching behavior.
Yes,
right?
Exactly.
So
but
implying that the vectorization should stay the same before and after the switching behavior, or maybe it should vectorize differently before and after. Right. So before the switch, before the semicolon, it needs 64 bits at a time, and after. So you're making an assumption.
That is true. So I'm making a plausible assumption, but doesn't need to be. But so the thing is that if I don't do this, I'm not going to produce a well-typed program in my sense. So I like to use types as a guidance that I have not screwed up something. So currently I type the sequence such that the input queue of the first component and the output queue of the first component are the same as the input queue of the second component and the output queue of the second component. And I express these in the types. So it is possible from an implementation point of view that I could choose different vectorizations, but I would have to modify my type system to allow more flexible typing for sec in order to be able to reuse types for this purpose. Yeah?
I wonder how can you enforce this kind of static property of known cardinality?
So all of the components of Wi-Fi except CRC
your programming model is pretty dynamic. Sometimes you can just emit, sometimes you yield, sometimes you skip. So
yes.
How do you know?
It's not very data dependent. So for example, a modulator takes two elements in and emits 4 elements out. It's kind of fairly obvious from the code. So I have to create all possible sets, and maybe I will lose. Maybe there is not going to be a way to combine the vectorization of the first component in a sec with the vectorization of the second component in a sec. In which case, I'll fall back to the the 1 and 1, which was originally well typed. So.
Can it be data dependent?
Sorry?
Can it be data dependent? So you say if x is bigger than 2, then
emit. But where x was one of the in your data stream. Typically, they're not data dependent. No. Typically, they are not data dependent. These blocks. So
in your language, you could program that.
You could program that. In that case, I would say unknown cardinality, and I would not vectorize.
Okay.
So the cardinality is a conservative but safe analysis.
Exactly.
Okay. It's better than streamlit, where it's not really enforced.
So transformer vectorizations. So without loss of generality, every Ziria. I mean, you can think of it. This statement is not quite accurate, but every Ziria transformer can be treated as a repeat of some computer. For example, the map is like I take 1 and I emit 1. So let's just forget about the primitive transformer map. Let's just think about a repeat of a computer. So how do we vectorize a repeat of a computer? Well, suppose that we are able to figure out that it has cardinality A in and cardinality A out. Suppose that we can do that. So, okay, we can vectorize the divisors of A in and the divisors of A out as before. Because we know that we cannot take and emit in each iteration smaller number than before. But we can also vectorize to multiples of A in and A out. I'm going to explain this in a second. Why do I say that we can vectorize to multiples? Well, he's a transformer. He's never supposed to finish. So you just pass data in and he just emits data out. So okay, I pass arrays of 4 elements in, and he gives me arrays of 8 elements out. That's okay, or 16 and 8, or it doesn't matter. Now, one possible way to kind of do this is, for example, I'm going to describe this by example. Here we can take 1 and emit 1, and what we can do is like twice. So we can take 8, and twice we can generate an array of 4 elements and emit it. So we have converted ST int to ST array 8 int to array 4 int. So there's something strange going on here in the sense that this guy, in a single iteration repeat, preserved so it had a rate of 1 to 1. This one, in one single iteration of the repeat, has taken 1 and emitted 2 components out. So that's a little bit strange and might hint to something. But if it's a transformer, it doesn't matter. You can just do it. Now, I said that it's a transformer, so he's supposed to always have data to process. It's going to run forever. However, let me question that assumption, because that transformer could be composed downstream with a computer. So the computer is going to say, oh, I'm going to finish processing at some point. So the amount of data they're going to pass, that this guy is going to process, is not infinite. So here's a concrete problem. Assume that this is a computer, and he just wants to take an array of 4 elements after vectorization. Just that. And assume that this guy here, in every iteration, takes 1 and emits 1. Okay? The quiz is it safe to vectorize this guy to take arrays of 8 and emit arrays of 4? And the answer is that it isn't. And the reason it isn't is because he's going to need 4 elements. So he's going to ask him for 4 elements, for an array of 4 elements. And in order for this guy, this poor guy, to produce 4 elements, he has to produce all, he has to consume all 8 to be able to produce 2 arrays of these 4 elements. So what is going to happen is that repeat of C may consume, if we do this vectorization, repeat of C may consume data that is destined for C2 after the switch. So this, we have the danger of this guy consuming more data than what was necessary. So we're going to lose data. So the solution is to make sure that we vectorize in a specific way that doesn't increase the rate, that doesn't decrease or increase that makes sure that we don't take less frequently than we emit, if there's a computer after us. Now, there's a dual problem that I'm not going to get into, which is transformers after computers, and the solution is kind of symmetric, so I'm not going to get into that. So the question is, how do we choose kind of the final vectorization? In the end, we may have very different vectorization candidates, like 256 and 42 in between, and 256, and 128, and 64, and 128. How do we choose which one should we choose as a compiler? I mean, we have to choose one vectorization. And notice that 256 is higher than 128, but 64 is higher than 4. So it's not very clear which one we should choose. Well, actually, in this case, it is clear. I mean, so in general, we want to prefer fat pipelines. But the idea is that we want to prefer fat pipelines that are kind of as uniformly fat as possible. This one is not a very uniformly fat pipeline. It's going to take the 256 bytes in, and it's going to emit them like it's emit 4x4 in the output. So we're not going to gain a lot in the interpretive overhead. This guy is kind of a struggler in the processing. Whereas this guy is going to take a chunk of 128, he's going to do his own internal processing, and he's going to twice emit, let's say, 64, for example. So the problem is that if we just maximize the sum of pipeline arrays, which would be a sensible thing to do, that's not good. 256 plus 4 plus 256 is greater than 128 and 64 and 128. So our compiler does instead employ a trick that's used in distributed optimization. Instead of maximizing the sum, we maximize the sum of a convex function, like a log function or kind of product of the sums of pipeline arrays. So in this case, it turns out log 256 and log 4 and log 56 is actually less than the log of the second pipeline. So it's just a heuristic, which seems to work reasonably well. So the final piece of the puzzle is pruning. So suppose that we get in our vectorization, so we get 2 vectorizations candidates that have the same type on the outside, like 8, 4, 4, 8, and 8 and 2, 2, 8. Well, in this case, like in the very end, that's happens in the very end. Actually, that happens locally. What we do is we prune by choosing for every type the one with the maximum utility that I described before. Right. So I just want to I think this is going to work. I want to show. This is my other. This is the compiler vectorizing the Wi-Fi receiver. My partner really loves this. Yes. So as you see here, it has computed. So this is output dumping output from the compiler. We have
Did you increase the font size?
I don't know how to do this very well in this. So I don't think it's very, very important. I just want to kind of show this in practice. Basically, you see this guy has taken 16 and emits 80. This data symbol has taken 80 and emits 64. Have pilot track takes 64 and 64. So various numbers have been generated by the compiler because of this optimization. So just wanted to show this as a proof that it works. So vectorization forms a very nice synergy with lookup table optimization. So this is the scrambler from the beginning of the slide. What we do is we vectorize, and after several transformations of the compiler, we get a code that maps this automap function, which takes an array of 8 bits and has a for loop inside that performs this imperative computation. This has been vectorized from 1 to 1 to 8 to 8. Now our compiler observes that this part here is an expression that has an input bit width of 15 bits and an output bit width of, let's say, 2 bytes. So actually, you can precompile the whole thing into a 64K lookup table. So our compiler is going to aggressively try to do this. And you can see that without the vectorization, the cost of actually, if we do it bit by bit, we would be able to have a lookup table, yes, sure. But the cost of actually going and doing the computation and looking up each and every single bit would make the lookup table not very efficient. So by doing vectorization first and then lookup table, we get a huge performance. Right, so very quickly, some performance numbers in the Wi-Fi. So these are the Wi-Fi specifications. This is